Good morning, one and all honors physics students. This is the Friday edition of Honors Physics. Just coming back to you from our home office here. This is Mr. Finn, of course, trying to get you a couple of lessons regarding sound. Yesterday, if you remember, we did a sound lesson on beat frequency where we had two tuning forks and they were sounded together at the same time. And they were almost the same frequency, but one was just slightly higher or slightly lower than the other, and we heard an overriding wave pattern, beat frequency. To find the beat frequency, we just needed to subtract the two frequencies of whatever we heard, and that would give you the overriding wave pattern. Today, I'm actually going to do a quick demonstration regarding Doppler effect. So hopefully you guys have seen the car video on the Google Doc the car in the parking lot moving along. It's only about a 1-minute video, but that'll show you an example of Doppler effect, and I'm going to show you another example of that in just a minute or two. Real quick, you guys doing a great job sending your questions in to the email address I've got. I had one viewer who's not actually in our class, but I'm going to give a shout out to this guy, Dylan Echo 1 or EC1. Has made some comments on the videos I posted. Really appreciate you looking in on that, Dylan. Don't know who you are, but appreciate you commenting on the videos I'm making for my high school guys. Okay, so the Doppler effect. What is the Doppler effect? The Doppler effect is actually a perceived change in frequency due to the bunching up or the elongation of sound waves as they reach our ears. So, if you're a bear and you got big ears like this, or a dog, you might actually have this effect more pronounced. We perceive changes in frequency based on movement. So either the supplier of the sound is moving, which is called the source, or the observer of the sound, which would be us, maybe in most cases, is moving. So when either of those two things are moving, there's going to be a perceived change in frequency as the sound reaches your ears, based on the fact that those waves could get bunched up against each other or they could be stretched out. So I'll show you that in a quick demonstration here real fast. Okay guys, I've got a little personal alarm here on the end of the string, and you can see or hear that personal alarm is emanating one frequency. But if I move it around in a circle, you can hear the sound difference as it goes around in a circle. And you can hear the changes in the frequency, but when I stop it from going in a circle, it just emits the one sound. So we'll go over how this works in just a second. Okay guys, so let's revisit Doppler effect. A perceived change in frequency due to the motion of the source or the observer. So, I know this looks a little different than in your book. In your book, this equation looks like F equals F sub 0, 1 plus a ratio of V sub O over V sub S. I tried to work it a little bit differently, so just follow me here. I think this might make a little more sense. F, which is your heard frequency, the frequency that you are going to hear, is equal to the original frequency times a multiplier based on the movement. Well, that multiplier has to do with the speed of sound, because the speed of sound in dry air is about 331 meters per second. Plus or minus, well, plus rather, 0.6 meters per second for every degree Celsius above 0. So on a normal 20 degrees Celsius day, 20 degrees Celsius times 0.6 meters per second for each degree Celsius makes that speed of sound right around 343 meters per second on a normal day, 20 degrees Celsius, like in our classroom, for example. So V plus V sub O, that's the velocity observer, over V minus V sub S, that's the velocity of the source, where V in both cases is the velocity of sound. So, an important note, both V sub O and V sub S are positive numbers if they're approaching. So if the source is approaching you, V sub s is a positive value. If you, the observer, are approaching the sound, like for example, you're getting closer to the sound of a freighter making a horn or a horn from a car, you're approaching, or an ambulance. Let's say you're traveling in a car and you're coming up on an ambulance which is stationary. You, the observer, are approaching. That's also positive. But both those values are negative if they are receding. So if you're moving away from the ambulance, then those values are negative. If the ambulance is moving away from you, then V sub s would be negative. But the formula remains the same. So in this denominator, if V sub s was a negative, then you'd have V minus a negative number, and that denominator would become bigger. So for example, if 343 was to minus a negative 20, well, that would be 363 in the denominator. I'll go through an example like that over the next couple of days. But today's example, a car approaching at 20 meters per second hits its horn, and the horn is going to be at a 300 hertz frequency coming out of the car. If the observers are standing still, well, what does this mean? Here's our formula. F equals 300 hertz times the multiplier 343, which is the speed of sound, plus 0 on top, 343 plus 0, over 343 minus a positive 20. Remember, we are approaching. The car rather, is approaching. The source is approaching. So 343 over 323 will actually give you a multiplier of 1.06. So that's what this whole thing in parentheses is, 1.06. Notice that the meters per second cancels on top and on bottom, so the multiplier actually has no units. Multiply that by the 300 hertz of the original frequency emitted by the horn, and you'll get 318 hertz. Now, we're not paying attention to significant figures right now, because if that was 2 sig figs, we'd actually be about 320 hertz. But if it's 3 significant figures, it would be 318, which is an increase in pitch. We would hear 318 when the car's actual value was 300 hertz. If you were in the car, you would hear 300 hertz. But if you're outside and the car's approaching you, you'd hear about 318 hertz. Now I'm going to go through a real quick visual on what those waves look like in just a second. Okay guys, I'm back with another visual on Doppler effect. So what I have here at the top is a car that's emitting some kind of sound out of some kind of antenna or siren. What I did was I tried to draw in visually what it would look like if you could see the longitudinal sound waves. So up here I've got a little compression right out of the gate, followed by a rarefaction where the sound waves are further apart, followed by a compression, followed by a rarefaction, followed by a compression. Instead of crests and troughs, longitudinal waves have compressions and rarefactions, kind of like the slinky that you guys saw, or the spring you guys saw in your lab. I'll try to follow up with a demonstration on that tomorrow, or Monday rather. Now what I have here is the green car is actually the same car at a time maybe a few seconds or a fraction of a few seconds into the future. So the green car and the blue car are the same, but the green car is the blue car at a position further as it's traveling. So the blue car is actually moving to the right and becomes the position of the green car at a later time. Still, the sound waves are being emanated from the car the same way. Compressions, rarefactions, compressions, rarefactions. While the wavelength between wave crests or troughs, like in a transverse wave, is the same as a longitudinal wave between the compressions. So a wavelength for a longitudinal wave might be the middle of a compression to the middle of the next compression. If we look up here, and this is my middle of my compression, and this is my middle of my other compression, the next compression, that my lambda will be the difference between those 2 points. Remember, lambda is wavelength. And if wavelength is big, frequency is low. Or there's a relationship which equals the speed of sound. Wavelength times frequency will equal v, the speed of sound, which we now know is 143 at room temperature. Now what about this next car? Well, it's also got its own compressions and rarefactions, which I did not draw the lambda for that. But if you can imagine, the green car, as it's emanating waves, are being pressed up against the wave fronts that it just emitted just a fraction of a second or a couple of seconds previous. So what's happening is those wave fronts are pushing up against wave fronts that were just emitted just a certain time ago. Now, if I take the compression in the blue, which was emitted a few moments ago, and this compression in the green, which was recently emitted by the same vehicle, and I take the difference between those two, well, you've got a much smaller distance. That will become the new lambda as somebody who hears these wave fronts crashing up against each other. So, the emission of the sound waves, the old lambda. The observer hearing those sound waves, the new lambda. And as we know, if lambda goes down, then frequency has to go up because the speed of sound is not changing. It's still going to be 343 meters per second in the medium of air at room temperature of 20 degrees Celsius. Okay. So as you can see, guys, Doppler effect, the observed change in frequency due to the motion of either the source or the observer is relatively basic. But you want to practice those problems a few times through. Now, I just did one where the source was moving and the observer was stationary. But the observer could be moving, or the source and the observer could be moving. I'll follow up with a few couple of examples on this in our coming week. But suffice to say, there's enough practice in there for you to get started. Just remember, V sub O has got to be positive if approaching and negative when receding. And the same thing for V sub S, but the V sub S is already subtracted in the denominator. Again, you can use my setup for the formula, or you can use the one in the book. They're both going to work out because V is the same on top and bottom. That's why you have the 1 minus the fraction in the Giancoli book. Anyway, guys, I'll see you Monday for our Google Meet for the 5th hour time. Again, that is Monday, 3:23 at 9 a.m. So if you guys are up and you need questions answered, or if you just want to fire some questions in through email, that's fine. I'll get to all that and we'll keep going. So when we meet again, it'll be Monday, and I'll have some more on Doppler, and I'll also have some stuff regarding sound moving into some different things there too. So keep in mind, Doppler effect for today, and I will see you guys after the weekend. Have a great weekend.